when we first learned how to solve differential equations, we started with a simple equation y prime equals a times y. And we were able to show that the solution is y of t equals a constant c times e to the at. You can verify that that is the solution by substituting it back into the differential equation. Now we want to solve systems of differential equations of the form y prime, where capital Y is a vector, is equal to the matrix A times y, where y again is a vector. Could it be so simple that capital Y of t is equal to e to the at times maybe a constant, we'll call that constant c? Well, that probably doesn't make much sense to you, because how do you look at the exponential of a matrix? What is e to the at? So that can't be the answer, right? Because there's no understanding that we have of the exponential of a matrix. Or is that the answer? We'll have to see that in a later video. But for now, let me try a slightly different guess that captures some of the same characteristics as our original solution to the differential equation. Let's make a guess that capital Y is equal to e to the lambda t times v, where lambda is an eigenvalue and v is an eigenvector. Now, if I want to verify that that is the solution to the differential equation, I'll need to substitute it back into the differential equation. So first, let's note that capital Y, if it's e to the lambda t times v, that's really e to the lambda t times a vector. We'll call that vector v1, v2. And so y prime, in this case, is going to be lambda e to the lambda t v1 and then lambda e to the lambda t v2, because v1 and v2 are just constants. And I've multiplied this vector by the scalar e to the lambda t. We can write that as lambda e to the lambda t times the vector v1, v2. We can think about that as being just lambda e to the lambda t times my eigenvector v. Now, what is a times y? A times y, well, that's going to be a, the matrix, done to e to the lambda t times the vector v. But e to the lambda t is just a scalar value, so I can factor that out. So it's e to the lambda t times av. That's going to be e to the lambda t times, well, since v is an eigenvector, av is actually lambda times v. And so, in fact, our derivative does match a times y. So our solutions can be written in the form y equals e to the lambda t times v, where lambda is the eigenvalue and v is the corresponding eigenvector. Let's see how this works in practice by trying to solve the differential equation y prime equals the matrix 6, negative 8, 4, negative 6 times y. Well, the very first thing that I need to do is I need to find the eigenvalues. So I'm going to take the determinant of a minus lambda times I. So that's the determinant of the matrix. 6, negative 8, 4, negative 6, minus lambda times the identity 1, 0, 0, 1. So we can think about that as being the determinant of the matrix 6 minus lambda, negative 8, 4, and then negative 6 minus lambda. Well, this becomes 6 minus lambda times negative 6 minus lambda minus a negative 32. We can rewrite this as negative 36. That's going to be minus 6 lambda and then plus 6 lambda for the inner and outer terms. So then plus lambda squared plus 32. So finally we get that lambda squared minus 4 is equal to 0. We can solve that to see that lambda must be plus or minus 2. So this matrix has two eigenvalues, 2 and negative 2. Now, let's find the corresponding eigenvectors. So for lambda equals 2, we have a minus 2 times I times v has to equal the 0 vector. So here we're trying to solve a minus lambda I times v is equal to the 0 vector. So I'm going to write this matrix, or I'm going to write this in matrix form. The system that I want to solve in this case is going to be it's going to be 6 minus 2, negative 8, 4, negative 6 minus 2, and then the right-hand side is going to be 0, 0. So I want to simplify this. So this is going to be 4, negative 8, 4, negative 8. The right-hand side is going to be 0, 0. And if I row reduce here, I notice that the second row is a multiple of the first row. So I really have just 4, negative 8, and then 0, 0 in the second row. Well, this gives me a free variable in the second row. So that means that I have some sort of choice. And so I'm going to say that my eigenvector, which corresponds to lambda equals 2, is going to be the vector 2, 1. Because you can see that if I multiplied 4, negative 8, 0, 0 times the vector 2, 1, I do indeed get 8 minus 8 in the numerator and then 0 in the denominator. So I do indeed get 0, 0. Now, because this is just one possible eigenvector, we can say that any constant multiple of this eigenvector is also an eigenvector. We get that because we have one free variable in this case that we can see with the row of zeros when we reduce our matrix. So here I have my eigenvector. We're just going to choose one and know that any constant multiple of that eigenvector is an eigenvector. And so I'm going to then move on to the second eigenvector. So here I'm going to let lambda be negative 2. We want to plug in to the equation a minus a negative 2, so plus 2I times v equals 0. So in this case, we're going to have that 6 plus 2, negative 8, 4, and then negative 6 plus 2 is our coefficient matrix, and then the right-hand side is 0, 0. This simplifies to 8, negative 8, 4, negative 4, with a right-hand side of 0, 0. And then we notice again that the second row was a multiple of the first. And so we have 8, negative 8, 0, 0 is our matrix, and the right-hand side again is 0, 0. And then this is sufficient information for me to come up with an eigenvector. Our second eigenvector could be the eigenvector, say, 1, 1. Here I'm using the fact that if I take my matrix 8, negative 8, 0, 0, and I multiply by the vector 1, 1, I will get 0, 0. So again, there are lots of choices for eigenvectors. I can choose any constant multiple of the vector 1, 1 as my eigenvector, but the eigenvector 1, 1 is simple enough, and so I'm going to use that one. I want you to notice that in both cases, when I looked at reducing this matrix, I got a row of zeros, and therefore I had a free variable. And that free variable is necessary because we are solving a matrix times a vector equals 0. And so if you want to have a non-trivial solution, you're going to need a free variable. If you're working with 2 by 2 matrices, it's going to be the fact that one row is going to be a multiple of the other row, so that when we reduce, we're going to get a row of zeros. So if you don't get a row of zeros when you reduce, then you know that you've made a mistake. Okay, so those are the eigenvalues 2 and negative 2 with corresponding eigenvectors 2, 1 and 1, 1. And so now what I've found is a fundamental set of solutions. I know I have two solutions here. The first solution is going to be e to the lambda t, or e to the 2t, times the vector 1, 1. And then the second solution is going to be e to the negative 2 times t times the vector. That vector is 1, 1. You'll have to excuse me, the eigenvector for the first one was actually 2, 1. Okay, so corresponding to the eigenvalue 2 is the eigenvector 2, 1, and corresponding to the eigenvalue negative 2 is the eigenvector 1, 1. Okay, and those are two different solutions. Those solutions are going to be linearly independent because the eigenvectors are linearly independent. 2, 1 and 1, 1 can be easily verified as linearly independent, but because I had two distinct eigenvalues, 2 and negative 2, that were not equal to each other, that guaranteed that the eigenvectors were going to be linearly independent. So I have two linearly independent solutions. And so I'm going to take a linear combination of those two solutions, just like when we were solving second order differential equations. And that is going to be my general solution. So y of t is c1 e to the 2t times 2, 1 plus c2 e to the negative 2t times 1, 1. You can leave your solutions like that, or sometimes people choose to write 2c1 e to the 2t plus c2 e to the negative 2t, and then we could have c1 e to the 2t plus c2 e to the negative 2t. That's another way to write our solution. Now, C1 and C2 can be determined by an initial condition. So I'll just remind you of this important fact that if V1 and V2 are linearly independent, then the solutions e to the lambda 1 V1 and e to the lambda 2 V2 will also be linearly independent. You can show that using a Wronskian, but I'm going to give you that as a fact for now.